This will be revealed in about 15 minutes time, I think, so I will discuss it. Very brief note on the history of many worlds, really, and of the global perspective of quantum mechanics. The fact that everything is okay, even if we assume that the whole universe is quantum mechanical and we treat all objects under consideration quantum mechanically, including the apparatus, including all experimental physicists and all animals involved. And I think the bottom line is that this is a perfectly consistent view. It may not, of course, survive quantum mechanics, but I think some of these aspects of it will certainly be imported into the next theory, which can only be even more general than what we're discussing now. Anyhow, historically, in the early days of quantum mechanics, there was a lot of discussion about waves and particles, as you know, and one of the key problems that was debated at the Solvay meeting and all sorts of other meetings in the early days was, of course, the wave particle duality. And I think the question arose, which would go something like this. If everything really is a wave and behaves like the Schrödinger equation would suggest to us, then why in an experiment like this, where we have a cloud chamber and we have a certain emission of a particle, and when we do these experiments, why do we actually see straight lines? Why do they behave like particles if we actually quantum mechanically understand that they are waves? And this was actually resolved very quickly. I will take you through a sequence of this very briefly. And I think the people who ultimately resolved this are actually Everettians before Everett. I think this took place in the late 20s, I guess by about 1930. All of these guys understood what it means for quantum mechanics to be a universal description at that stage, and that there are no problems. But very briefly, I'm not a historian of science, so this is my own version of history as I read about it. So basically the question was, why don't we see something like this? If it's a wave, why do we see straight lines? And Heisenberg, you wouldn't be surprised, was the first person to comment on that. And I think there is at least about 8 different ways of saying this. And I think each physicist kind of understands all of them and is capable of arguing in this way. But let me give you the flavor of the argument. Heisenberg would say, when you have an alpha particle decay, then this alpha particle will indeed behave like a wave packet that will be spreading. But however, before it spreads too much, it will simply hit an atom in the background gas in the chamber, and this will localize it. I mean, you know, maybe he thought about this in a discontinuous way, but you don't need to do that. And that's the whole point of all of this. So basically, then you localize the particle, beyond which it continues now with the same kind of behavior. It spreads a little bit like a wave, then it hits another atom and so on. So basically, if the gas is dense enough, this will, of course, give us the illusion of a straight trajectory. And it's the same way that you argue for the derivation of geometrical optics when you use the wave optics that's based on Maxwell's equations. Heisenberg, of course, also used his uncertainty relations. Heisenberg had this very beautiful way of saying that quantum physics takes over the dynamics of classical physics. Those are the same equations. You don't really need to modify these equations. What you need to do is upgrade certain key entities into operators instead of just mere classical numbers. And here is how Heisenberg would have done it. You know, it's really primary school physics that the position at time t is the position at time 0 plus velocity times t. Then you can construct by multiplying both sides by the same entity a commutator, at which point you upgrade this to quantum mechanics, from which you derive the uncertainty relation and so on. So basically, that's one way of understanding how this classical trajectory will arise. There is a nicer way, actually, that I think, which is to think of it the way Huygens thought about waves. And here what I'm doing is I'm saying, imagine A is the size of your atom, S is the size of the spread of the particle as it propagates. D is the distance that the particle travels, and lambda is the wavelength of the particle. So this applies to anything. It could be a photon, it could be an atom, it could be an alpha particle, which is what they were trying to describe. And so this already tells you about the spread and how it's related to the confinement of the particle, the distance it travels, and its wavelength. Of course, you can look at when S becomes larger than A. This is basically when you start to see a significant spread, and this is something that we call the Fraunhofer limit. And this will tell you how long the particle will have to travel in order to start to spread. But actually, Heisenberg says, well before any noticeable spread happens, the alpha particle will hit and ionize one of these atoms, which will effectively localize it, and then the whole game repeatedly continues. Incidentally, you don't have to be a physicist to see that this formula is correct. This formula has 4 numbers that are relevant. Lambda is by far usually the smallest of them. D is by far usually the largest of them. And A and S are the 2 medium-sized numbers. So if I have to multiply 2 numbers and equate them to another 2, then the only logic is to multiply the medium-sized numbers and equate them to the smallest times the largest. And that's it. That's how every physicist actually derives things without doing any mathematics. Anyhow, joking aside, the people who took this very seriously, so Heisenberg had more this view of a single world and how a single world arises. But actually, in the same writing, he introduced what we call the Heisenberg Cut. And he said it makes absolutely no difference if you want to think of the background gas as also quantum mechanical. I can include everything in my quantum mechanical description, and the story will be exactly the same. And I think this was said much more eloquently by first Darwin and then by Mott himself. And basically what they said is exactly what Hamilton would have actually, how he would have described the mechanics of particles in analogy with waves. So he would say, here is the alpha particle initially spreading as a completely perfectly symmetrical wave in all directions, just like water waves. But actually within this picture, we can actually think of the following. If the alpha particle happens to excite an atom here, then, and you can use Heisenberg's logic to do this, you can simply solve the Schrödinger equation to actually derive this. Then the probability that the next atom to be ionized is along the same line is extremely high. Like I said, if the density of the gas is very low, you will start to see deviations. This is only the lowest approximation. But actually, according to Darwin and Mott, and I think they understood this as well as anyone, all of these rays would exist simultaneously. And so the statement is exactly as Everett would have liked it. You have a branch in which this atom gets excited, followed by this atom excited, and so on. But you also have a branch in which this atom gets excited, and then the atom in the straight line direction gets excited, and so on. And all of these things exist simultaneously. And both Darwin and Mott say that the thing is best treated fully through Schrödinger's wave mechanics. In fact, if you read later Schrödinger, his lectures in the late 40s would have been identical. He was an Everettian at least 10 years, I would say, before Everett. All of these guys understood it, I think, the way that we now understand this. And like I said, Hamilton, he just didn't have the experiments that forced him to go in the quantum direction. But actually, Hamilton very much thought of mechanics in this way. And I think we all know about that. So the wave fronts and the paths being orthogonal to these wave fronts. And here is now Everett capturing all of that and saying, yes, there is no problem with this view. The whole world is quantum mechanical, and we really don't have any problems to think of it like that. So what I like and what I'm distilling out of it, it's a little bit, I think, similar to what Chiara was saying yesterday, that there are certain messages that are really important here to absorb somehow. And One is that the measurement is simply just creation of entanglement between whatever you call an observer and whatever you call the system that is being observed. But it's a completely symmetrical state of affairs. The observer is just another physical system, and it really need not have any special properties. I mean, we humans may well have some properties that computers don't have, but as far as this picture is concerned, they are probably by and large irrelevant as far as we can see. We don't need to postulate anything in addition. And now I'm almost quoting Schrödinger straight from Schrödinger's writing later. This is the later Schrödinger, who said, this avoids collapses, quantum jumps, any discontinuities. There is no spooky action at the distance at all. It's all nice and local. As we heard yesterday from Paul and from various other people, and actually that's the message I want to drive home now, very briefly. So basically, the confusion here is really more a grammatical confusion of sorts when people say quantum mechanics is non-local. What practitioners like myself mean by this is that it's Bell non-local, in the sense that Bell gave us this choice that by having entangled states and by making local measurements on each of the two particles that are entangled, I don't want to dwell too much on this because everyone knows this. I think all the people present here are as expert as anyone else. But Bell told us that violation of his inequalities forces us to give up classical reality or the notion of locality. And basically, you know, most of us, I would say, would probably vote to keep locality because there is no indication whatsoever that this is being violated. And I think most of us would agree that the classical notion of reality, where everything is described by numbers, cannot be maintained. It simply cannot be. So a simple way out of it is, and I think Paul himself alluded to this, a simple way out of it is to say we do keep reality. It's not that we don't want reality, but it's a reality based on Q numbers and not simply on numbers, on real numbers, if you like. And it's a very simple argument. You know, if you take an entangled state, like a singlet state, spin up and spin down, anti-correlated, then of course, whichever direction you choose to measure this in, these spins are always anti-correlated. So if you do assume that the value of the spin exists independently of you making a measurement, the classical value exists independently, then you are forced with the question of how does the other spin know which spin I will measure here, which direction I will measure here. So it's very clear immediately that something non-local has to be postulated if you want to hold on to the classical reality. And actually, this was also mentioned that Asher Perez had a very colorful way of explaining this by saying that unperformed measurements have no outcomes. So that really simply means you cannot assign a real number. You can only assign a Q number, as Dirac called them. You can only assign an operator to this entity, and that's the only thing that really has a reality. And what I'm saying may be a surprise to some people, but it is no surprise to any quantum field theorists. This is exactly what quantum field theory is all about. And I want to take you very briefly through this. So the reason we've heard a lot about also the Schrödinger and the Heisenberg pictures, and actually it's immaterial which picture you use, you will have to reach the same conclusions. You can do quantum field theory, even though Heisenberg picture is more natural, you can do it with the Schrödinger picture, and it's a bit more cumbersome mathematically speaking, but you will get there. You will preserve all the properties that we know and like. But I just want to say, here is another way of saying why some people feel that there is something non-local with quantum mechanics. Mistakenly, they feel mistakenly that it's non-local. It's not non-local, but it's this simple property that we call phase kickback in quantum computing. So I have a single photon here, going through the usual Mach-Zehnder interferometer. And I kick in a phase in one arm of the interferometer. Of course, this could be any other particle. It doesn't have to be a photon at all. And then as you do another beam splitter, you basically detect your probabilities. And as you know, you get sine squared of the angle and the cos squared as different frequencies if you were to repeat this experiment. But now I'm going to do analysis in the Schrödinger picture, where the state after the first beam splitter is 0, 1 plus 1, 0. I'm already using a field theoretic notion where 0 means the vacuum state. So 0 just means one arm has no photon, the photon is in the other arm, plus vice versa. That's how you would, in the second quantized notation, write the single photon being superposed across two arms. And now I'm saying if I kick in the phase in the upper arm, which corresponds to this number 1 here, what the Schrödinger picture doesn't tell me is where the phase is kicked in, of course, because I'm not telling you what the operators are doing. I'm only tracking the wave function here. And actually, if I were to write the phase in front of 0 instead of in front of 1, I would get exactly the same Schrödinger state. And even worse, because the global phase cannot be detected, this phase could equally well have been kicked into the other arm of the interferometer, and you wouldn't be able to tell. Your output probabilities would be identical if you were to kick in the phase in the upper arm or the lower arm. And this somehow mistakenly leads some people to say, wow, it's non-local, spooky action. I kick in the phase here, suddenly it's in the other arm. But that's because you are looking at the wave function only. The way to treat this, and this is what any field theorist would immediately do, is to think about what happens with operators. And here I'm doing a very simple, it's an extremely instructive exercise to do the whole calculation in the Heisenberg picture. Here is the electric field, or whichever operator you want to choose. In the left-hand arm of the interferometer, A plus A dagger, and A plus A dagger in the right-hand arm. After the phase shift, you can see that the phase shift has been kicked in only in the left arm, not in the right arm. So I'm tracking all the relevant operators which pertain to the two modes of the light field, but it could be matter field, it's the same analysis. And it's only after the second beam splitter that your phase actually gets mixed in and exists in both of the arms, output arms of the interferometer. And needless to say, when you do the expected value with the Heisenberg state, with the state that doesn't change in time in this picture, you will of course get exactly the same cos squared and sine squared probabilities. But the point here is that in order for you to see how the phase is locally imprinted in one arm, and then how it gets across through interaction, through mixing into the other arm, you really must follow the operators. And that's exactly what quantum field theory is all about. So now I can very briefly, before I go into the second half, tell you about the title of my talk. What these operators, according to a quantum field theorist, are the only elements of reality. They always exist. Every point in space has all the relevant operators pertaining to all the relevant fields that we think of as fundamental in this universe. So it's very hard to imagine that, because now I was just imagining the light field, the electromagnetic field existing at every point in the arm, each arm of the interferometer. But you have to think of the whole universe as being made up of these Q numbers, each of which describes different aspects of different field. And that's it. That's the reality. That's what exists. And then I said, when we get entangled to make a measurement, somehow through our entanglements, we pick up only some aspects, and the other aspects become inaccessible to us. That's why I kind of say the world only exists fully when it is not measured. And when we measure this, then of course we are stuck in one branch until someone else if they are able to decide to interfere us. And I will get back to that exactly now. I've written a number of times with this. I think the paper with Chiara and Nisetu is a recent paper that may actually be a very simple introduction into how to do these things. But let me make this final comment that there is no non-locality in quantum physics. I don't want to bore you too much with this. I think, like I said, it may be surprise to some people here, but if I said this to Wilczek or Weinberg, they'd probably be yawning and they'd be saying, of course, please tell us something new. Please tell us something we didn't know. Anyhow, now I want to upgrade this to this other statement that I think Tony very kindly attributed to me, but I think it's his statement. And the statement, so I think quantum mechanics is beautifully captured by these two statements. One statement is that unobserved measurements have no outcomes, like I already said. Incidentally, Asher Perez would have been militantly against many worlds. So I think I disagree with him on all these other aspects, but I think this statement beautifully captures the message of Bell's inequalities and quables, you know, the quantum observables, quantum beables, if you like. So what I want to do now is comment on this second statement that Tony made, which is that even the outcomes that we do not observe in this world could actually affect future measurements. And if quantum mechanics is true at every level, this has got to be true. It's just a simple consequence of quantum mechanics. So this is my very simple-minded presentation of what you've heard zillion times already about. It's Schrodinger's cat. Here is a snow cat. I think this is what my students make when I send them to a winter school in Les Houches. They're having fun outside making dead and alive cats. And as you know, this is what Schrodinger would have said. As soon as you have a microscopic system in a superposition, like a photon in a beam split, in an interferometer, and as soon as you couple anything to this, then this anything, I think Chiara called it the totalitarian principle of quantum mechanics. This other object, in this case, a cat or anything else, will have to become entangled to it and will basically end up being in a superposition of these two possibilities together with the system that is being observed. Now, of course, the difficulty of doing an experiment with this, it's easy creating this, but I think what's difficult is re-interfering these two branches. And that's, of course, the big question. Is this fundamentally impossible? I don't think so. I think everything suggests to us that this is possible. Of course, it may require a lot of effort, a lot of resources, but I think ultimately it's just a question of money, really. And now what's interesting here is that the same story, and I think Tony beautifully said it, that this leads to different observers simply having different perspectives, depending on where they end up being part of this very big entangled state. So here is an experiment that's a variant of Schrodinger, and it's David Deutsch's variant of Schrodinger, which I think captures this very beautifully. And the variant is there to say that there is no contradiction with us seeing definitive outcomes, while at the same time existing in this very big entangled state in the multiverse. These two statements are simply not contradictory. In fact, they happen to be true if quantum mechanics holds at this macroscopic level. That's always the big if. So now, instead of a cat or a dish, in addition to this cat, I'm going to have a human observer, Bob. And Bob will be observing this experiment inside the laboratory. And I will have another human, Alice, who will be controlling the whole laboratory. Now you can say, why are you making this so needlessly complicated? And the only reason I can think of is that I need a human because as far as we know, humans are the only other animal with which we can faithfully communicate. I mean, I'd be very happy with a bacterium. I'm happy with a cat, but I don't know how to communicate with cats in a faithful fashion that I really, I mean, I can talk to cats, but I don't understand what they're telling me. I mean, I talk to dead people as well, but they never talk back. So I need another human simply because I want to understand what it is that they are telling me. That's the only reason. Otherwise, and I think what David imagined is you can do this with artificial, you can do this with a computer, you can do this with an AI. And in fact, I will make a comment in about 10 minutes time about this because I think it's relevant to our discussion as well. So now here is Bob, and quantum mechanics suggests to us that there are two, when Bob has looked at the cat, Bob splits, if you like, for lack of a better expression, into two branches, and in one of them, Bob is very happy because the cat is alive, and in the other one, Bob is very sad because the cat is dead. Now, what Alice wants to do is Alice wants to really confirm that Bob sees a definitive state of affairs, and that's the key, while not collapsing, that's one way of putting it, or another way, while not getting entangled to the system herself. She wants to avoid being Veganist Friend, if you see what I mean. She wants to stay detached so that she can re-interfere everything at the end of it. And that's interesting. So what David envisages is the following. Alice writes on a piece of paper a question for Bob that she puts underneath the door. And she says, do you see a definitive state of Felix? I'm calling the cat Felix now. So basically the question is the same. And when it goes to Bob, independently of which branch Bob is in, he will write yes on that piece of paper. Because in one branch, Bob sees a dead cat, it's a definitive state of affairs. And in the other branch, Bob sees an alive cat. And so he would say yes. So this is a clever way, if you like, in which Alice can make sure that halfway through this interference experiment, Bob sees a definitive state, even though Bob himself is in a superposition of these two different, there are two Bobs, if you like. I mean, our language becomes a bit more colorful when we are describing these things, but there is no physical ambiguity, if you see what I mean. So now this is a theoretician speaking, all Alice needs to do is re-interfere these two possibilities. And of course, that's exactly the difficulty here. And many people would object here that even if this is possible, it could actually be very difficult to do simply because of all the resources involved. So basically, in order to complete the interference, remember, every interference experiment is applying a unitary transformation U to create the superposition, and then applying U dagger to re-interfere these two possibilities. And if you come back to the same state you started with, you've effectively performed what we call a perfect interference experiment. That's all we ever do. All quantum physics experiments are U followed by U dagger. That's it. I'm not exaggerating. Some of them are just extremely complicated, like the one here. So you can already see what the difficulty is. The interaction of the cat with the photon, then Bob with the cat getting entangled to the photon, all of this has to be undone, let alone if you think that the cat dies in one branch, if it sees a photon going there. That means the cat has to be revived and has to be alive at the end of the experiment. A friend of mine calls this operation the Lazarus operator. So it has to bring the cat from the dead. So that's why, there's no point in really talking more about this because it may simply be completely inconceivable. But the bottom line is that logically speaking, we are talking about simply 3 quantum bits worth of experiment. You need 1 quantum bit for the photon, another quantum bit for Bob, and yet another quantum bit for Alice. So logically speaking, it's an extremely simple experiment, providing that you can control it very well. And in fact, coming back to David's point, it may well be that we don't need more than 1,000 fully coherent quantum bits to simulate a conscious entity? We don't know that. I mean, this is all wide open. So I'm not even going to speculate about it. I have no idea. But maybe you can do the whole thing with a computer that simulates artificial intelligence. And all it takes is 1001 atoms to perform exactly this experiment. And you will confirm all of this. So there's no point in us speculating which way this would go. Is it possible or impossible? I think everything we've done so far suggests to us that one day this may well be possible. We don't know. We have to keep going in that direction. So now, halfway through the experiment, what's interesting is that Alice can confirm that Bob is entangled to the cat, to the poison, to the photon. All of them are entangled. They're in this highly entangled state. Topologically speaking, this is something that we call Borromean ring. Each of these links is connected with the other link until you erase one of them, and then they all fall apart. They are no longer entangled. This is something that we call a GHZ state, or Veganist Friend. And so it's very interesting that Alice can actually confirm a superposed state without collapsing it, without entering that entangled state. And let me add yet another twist on the tail. She can even communicate this to Bob now. So halfway through the experiment, when Alice sees that Bob said yes, in both of these branches, Bob sees a definitive state. She can now write subsequently on a piece of paper. She can say, I know, dear Bob, that you see a definitive state, but let me tell you that there is another branch in which a copy of you exists that sees the other outcome. This is exactly the unobserved outcome that can affect future measurements. And that's actually what Tony had in mind. And that's the way it is if quantum mechanics holds at this level. So here is Alice telling Bob that he really is in an entangled state, even though to him, it doesn't feel like an entangled state at all. So if you didn't tell Bob that he's in an entangled state, and you ask Bob to predict what's going to happen when he goes through the final beam splitter, in each branch, Bob would say, I'm going to end up statistically 50-50 at each of the outputs of the final beam splitter. But that's not what's going to happen here. He's only going to come out one way, the way he came in, if quantum mechanics is correct. And the only way that Bob can predict this is if he knows that he is in this superposed state. So when Alice tells him now that he is in both branches, he will be able to conclude correctly about future experiments. Otherwise, he gets surprised. It's very interesting. So let me not dwell too much on these things, but for those of you who are not familiar with the logic of this experiment, why you can do this, it's effectively a parity check. What Alice needs to do to confirm that Bob is in an entangled state is basically equivalent to a controlled swap gate in quantum. That's why I said you can do it with 3 qubits. 1 qubit is the control qubit, and the other 2 qubits are Bob and the photon, if you like, or Bob together with the cat, or cat together with the photon. It doesn't matter how you partition this. And actually, it's the same logically as this classical riddle of having 2 brothers, which are correlated in the way that one always lies and the other one always tells the truth, but you don't know which one is which. And what you have to extract from them is a certain true statement, but you cannot know which of them is a liar and which of them is a truth teller. So, and there is a way of doing that, but you have to ask a question which correlates the 2 outcomes. And this classical gate, the quantum equivalent of this classical gate, is exactly what Alice needs to do to confirm that Bob is in an entangled state. That's kind of the logic of that. It's just a quantum logic in this case. And of course, needless to say, There could be yet another. I'm continuing with the Alice in Wonderland analogy. There's Mad Hatter. There could be other observers, and each of these observers will have their own perspective, as Tony said. Each of them will have their own clocks, their own spaces, times, all of that, and none of that is ever in contradiction with quantum mechanics. In fact, that is exactly the message of quantum mechanics. That's what's interesting. We just need to be able to test it at the more and more macroscopic level. And now the final thing along these lines is the following one. So then I will make a few comments, and I think I will wrap it up. Hopefully I'm on time. The final thing, and this is what sometimes people think it's a puzzle, but again, I just want to say it's not a puzzle at all, is that Alice, and I don't think this should come as a surprise to you, Alice can, even if she can control Bob, she can convince Bob that quantum mechanics is completely wrong, actually. And so let me give you that scenario. That also is a consequence of quantum mechanics. Now I'm going to use quantum mechanics to prove that quantum mechanics is wrong. And I'm claiming there is no contradiction in what I'm going to do now. So Alice gives Bob n qubits, n is a large number, all prepared in an equal superposition of 0 and 1. Each qubit is identical and prepared in an independent from others superposition 0 plus 1. And then Bob is told to measure each of them individually in the 0-1 basis. And now, if we are right that quantum mechanics holds at the level of Bob as well, there will be 2 to the power of n Bobs in each of the 2 to the power of n universes, each labeled by one of the 2 to the power of n strings that actually corresponds to the outcome of measurements. There will be a universe with all zeros, and Bob will be looking shocked there. It's like tossing a coin and getting 100 tails, and someone told you it's a fair coin. And there will be all other universes. Majority of them obviously will be the typical ones, as we call them statistically. But Alice, remember, Alice controls the whole experiment. I'm assuming Alice can apply any unitary transformation. And in this case, Alice will do what we call amplitude amplification. Alice will simply run something akin to Grover's search algorithm that will amplify the branch which contains all 0 outcomes. And that's it. That's the only branch in which Bob now exists with 100% probability. So Bob comes out of the laboratory and he said, "Gosh, Alice, I violated quantum mechanics. They all came out in a state 0, and you told me you gave me an equal superposition of n of them." And that's it. That is the conclusion. There is no other punchline here. Anything is possible if Alice has this kind of control. And like I said, you know, it may be a long time before we are able to do this with a conscious human observer. But actually doing this with a quantum computer with 1,000 quantum bits is a reality already. That's exactly how this goes. We know we can do these things with near certainty. So now between 1,000 qubits quantum computer and a human being, is anything dramatic going to happen that forces us to abandon quantum mechanics? I have no idea. But I think whatever comes next, I think something will come next, but I think it's going to be even weirder than quantum. It's not going to be a return to classical probabilities and correlations and all of that. Anyhow, this is, so by the way, the same is true classically. If the world was completely classical, and if Alice has the power to re-engineer your brain whichever way she wants, then she can convince you of anything she likes. So there is nothing peculiarly quantum about this. All I'm assuming is that I have a power to really deterministically control a large part of the universe. There's nothing contradictory about this. Anyhow, when people talk about Veganist Friends, this is only a tiny, this is the Mott scattering, the alpha particle scattering picture that I gave you. This is only a tiny, tiny aspect of quantum mechanics, in which we have orthogonal branches that we can clearly identify. Each of them we can think of as a classical world, and all together they exist in a superposition. But this is just one approximation. Of course, we, being macroscopic and through our perception, seem to see the world in this way. But of course, all our microscopic experiments are telling us that the universe is very different, and possibly even at the macroscopic level. So Veganist Friend is just one of those very special GHZ-like states, but quantum mechanics applies to any other states in between that are non-orthogonal and everything else, just like in the alpha particle scattering. And now I want to finish with this nice picture. Again, it may be a long while before we may be able to do any interferences at this level. But this is another thing that I actually learned from David, but it's to do really with Page and Wouters. Frequently, when you talk about other universes, you get the question of how does it feel to be yourself in another universe, you know, as though this is a very profound mystical statement. I think these are usually questions from people who read Philip Pullman a lot, you know, and they get the impression that you can hop from one universe into another, remember the previous universe, go back, and all that nonsense. You know, that's not, of course, what quantum mechanics is all about. But actually, at the level of the universe, this Page Wouters picture is beautiful because it answers the question in exactly this way. What does it feel like to exist at another time? So, you know, if someone says to you, how does it feel to be in the other branch of the universe? You could just say, give yourself 10 minutes and then see how it feels. And that's it. That's exactly how it feels. You know, there's nothing unusual about that. And I'm hoping, you know, some of these things may not sound conventional to you, but I really am just communicating quantum mechanics as it is. This is what it is all about. Whether we will be able to control things at a higher and more intricate level is a wide open question. And I'm very open to quantum mechanics failing. Actually, I am praying on a daily basis that it fails, because that would be a great news. It's been boringly consistent for 150 years. But actually, the failure will signal something even magical, if you like. It's certainly not return to classical determinism. To bring things down to the very boring and mundane level, this is how far we are planning to go in the next few years. And this is my last slide, actually. So forget a cat, forget Bob, forget all of these things, artificial intelligence at the moment, that's all very distant, let's say 10 years plus. What we are trying to do within the next few years is the following experiment. We've done half of it actually by now, and you can read about that. These are published results. But what we would like to do is take two living systems, put them into optical microcavities that are separated. Let's take two viruses. I'd love to do this, as you can imagine, with the coronavirus as a revenge, you know, a dead than alive coronavirus. But anyhow, better dead probably than alive. But anyhow, what I'm doing here is I have a Mach-Zehnder interferometer, and in each arm of this interferometer, I have a living system. Ultimately, we will probably do this with a non-living system as a warm-up, as a calibration, already difficult enough. But what you want to do is send a single photon, which then, if it gets absorbed in one cavity, it excites one of these viruses or bacteria, and it doesn't excite the other one. Whereas if it gets absorbed in the other cavity, it excites this system here, but not the other one. And you can see that in our language, I'm preparing an EG plus GE, maximally entangled state of two living systems. Is this possible? Almost certainly yes, in my view. It really is a question of money. If you give me enough research funding, no doubt we can do these things at that level. Of course, it would be much easier to first do it with a simple organic molecule of smaller size, simply to eliminate all sorts of noises, to do it at cryogenic temperatures and so on. But basically the idea is exactly Schrodinger's. It's stolen directly from Schrodinger. Take a single system, make it in a superposition of states, couple it to something else, and that something else then inherits this quantum ambiguity. And I think we are very close to being able to make entangled states of two living systems. And if this works out the way that quantum mechanics suggests, then you can draw your own conclusions, of course. Needless to say, I'm ignoring all sorts of complexities as to how this would be done, how we would confirm that it's entangled, and all sorts of things like that. But I'm very happy to talk more about it during the discussion time. So let me just leave you with the conclusions. As far as we are concerned, as far as we can tell, quantum physics really does seem to apply to objects at all scales. Again, I'm talking more as a microscopic, atomic, molecular, quantum optician, if you like. I don't know about astrophysics. It could be that there are some huge surprises there that will make us reconsider foundations of both quantum physics and general relativity. But from the micro side of things, the level that we are talking about, chemistry and biology, we really don't see any surprises. We just have to keep going and maybe something happens. This is an interesting one. I like this because it makes no difference. It's a very democratic picture. All physical systems are the same. There is no difference between the observers and the observed. And even, like I said, I commented on the fact that time itself could be seen to arise out of this sequence of quantum universes in this page Wouter's picture. Now, the final thing I want to say is that we really do live in exciting times, because many of these speculations that I talked about were there even in the 30s, 40s, 50s, 60s, from various directions. People thinking about chemistry and biology, but also thinking about quantum gravity, made all sorts of predictions of this kind. But we are now genuinely at the level where we can begin to test this experimentally. And I think it's a fantastic, people say this century is the century of biology. The last one was the century of physics. I think they're completely wrong. This too is the century of physics. And it's physics going into chemistry and biology and more macroscopic and explaining all of these things and seeing how it relates to that. So I'm very excited to be alive at a time like this. Thank you very much for your attention.
Thank you very much, Vlatko, for the wonderful talk. We have 2 minutes for a short question. There was Don Page who had his hand raised since a while. So Professor Page, if you want to unmute yourself and ask your question.
Yes. Okay. Well, very, very nice talk. I just wanted to make one thing that I think was a minor error. You said that that only the cubables exist, only these operators. But I would say that there's also the quantum state of the universe that gives expectation values for the operators. So I would
absolutely right. Yeah, absolutely right. And actually, you could see in my practice when I was calculating this for the Mach-Zehnder interferometer, I had to take that average with this state of the universe that doesn't change. You're absolutely right. I agree.
Yeah. And the other point is that maybe Alice, it might be simpler for Alice just to manipulate the part of Bob's brain where he believes in quantum mechanics. That might be easier than that. I mean, just like I remember the movie version of Contact that this woman came back from with this long hiss on her recording device that was supposed to be some indication of time traveler. It occurred to me it would be much simpler for these people just to manipulate the tape that she had. I mean, why they don't need any.
Yes, Don, I love the movie as well, and I think you are absolutely right. This goes in the direction of Boltzmann brains. What is more likely to have happened, or what is easier to create? I think you're right. Yeah.
Okay, so this is a good time to end the recording.